Chapter 6, Chemical Composition. How much sodium? Sodium is an important dietary mineral that we eat in our food, primarily as salt, table salt. Sodium is involved in the regulation of body fluids, and eating too much of it can lead to high blood pressure. The FDA recommends a person consume less than 2.4 grams of sodium per day, and most of this sodium intake comes from the salt we use to season food. The chemical composition of sodium chloride table salt is NaCl, 1:1, one sodium ion to every chloride ion. So actually only a percentage of salt is sodium. The rest is chloride. This information from the formula masses and from the periodic table can be used to calculate the mass percent of sodium in salt, and we'll work on this a little later. Atoms are way too small to count, so we have to count by weighing. An example of this is hardware stores sell nails by the pound, which is easier than selling them by the nail. Customers often need hundreds of nails, and counting them takes too long. A customer still needs to know the number of nails contained in a given weight of the nails. This problem is similar to asking how many atoms are in a given weight of an element. The hardware store customer buys 2.6 pounds of medium-sized nails, where it's known that a dozen of these nails weigh 0.150 pounds. How many nails did the customer buy? The solution map is simple. We're given the pounds of nails that he bought. We can convert that to dozens of nails because we know 1 dozen equal 0.15 pounds, and we can convert the dozens of nails to actual count of nails because we know 1 dozen is 12. So the simple setup is following our conversion factors, and factor label method is what we're given. The conversion factor with the pounds in the denominator to cancel this. The numerator is dozen, and then again the second conversion factor, resulting in 208 nails for the 2.6 pounds the customer bought. Counting by weighing atoms by the gram. With atoms we must use their mass as a way to count them. They're too small and too numerous to count individually. Even if you could see atoms and count them for 24 hours a day as long as you lived, you would barely have enough time to count the number of atoms in something as small as a grain of sand. Counting by weighing atoms by the gram. With nail we used a dozen as a convenient number for our conversions. A dozen would be too small to use with atoms, even a gross, which is 144. We need a large number because the atoms are so small. The chemist's dozen is called the mole and is abbreviated MOL. Not much of an abbreviation. So 1 mole equals 6.022 times 10 to the 23 by count. A mole of anything is 6.022 times 10 to the 23 units, just like a dozen is 12. This number is called Avogadro's number, named after Amedeo Avogadro, pictured here. So to turn from count to mass, we use the concept of a mole. A mole, 6.022 times 10 to the 23, is Avogadro's number. Any idea how big that number is? Here it is, written out in regular notation. It's 602 sextillion and 200 quintillion. It would actually take about 20 quadrillion years just to count this number. Well, I don't know who would do it because the age of the Earth, estimated age of the Earth is 4,500,000,000. So it's very big. On your calculator, remember that you must use scientific notation and enter by pressing the key 6.022 EE, enter the exponent key 23. A mole of atoms or molecules generally makes a reasonable size object in our world. 22 real copper pennies is about a mole of copper. 2 large helium balloons is about a mole of helium. The size of the mole is empirically measured quantity. The numerical value of the mole is defined as being equal to the number of atoms in exactly 12 grams of pure carbon-12. This definition of the mole establishes the relationship between mass, the grams of carbon, and the number of atoms, Avogadro's number. This relationship allows us to count atoms by weighing them. An example. Let's convert moles to number of atoms. Convert 3.5 moles of helium to the number of helium atoms. Are given 3.5 moles of helium, and what we want is the count. Here's the relationship. 1 mole is equal to 6.022 times 10 to the 23. The map looks like this. Start with the given moles of helium and end up with a count using this conversion factor. Here's the setup again. According to our given 3.5 moles, the conversion factor arranged so that moles cancel, and you end up by multiplying to get this number, 2.1 times 10 to the 24 helium atoms. How do you convert the number of atoms to moles? Well, suppose you have 1.1 times 10 to the 22 silver atoms, and you want to find out how many moles that is. Start with the given, the number, the count. Use the mole conversion factor. 1 mole of silver is 6.022 times 10 to the 23, Avogadro's number. And set up the conversion as you're used to. Given, conversion, making sure that these cancel. And you end up with 1.8 times 10 to the minus 2 moles of silver. The pictures here I've shown, they have the same number of nails, but the weight of 1 dozen nails is different is heavier for these than for the smaller one. So it is with atoms. The same number of atoms for different elements, they're going to weigh differently. For example, a mole of sulfur is 32 grams, pictured here. A mole of carbon is 12.01 grams. The atomic mass unit, AMU, is defined as 1/12 of the mass of a single carbon atom. The atomic mass of any atom is equal to the atomic mass of that element expressed in atomic mass units. For instance, 1 copper atom has atomic mass of 63.55 AMU. You can see this number on the periodic table under copper symbol. The molar mass of any element is equal to the atomic mass expressed in grams. So 1 mole of copper has a mass of 63.55 grams. The molar mass of copper is 63.55 grams per mole. And the number of atoms in any molar mass quantity is 6.022 times 10 to the 23 atoms. The mass of 1 mole of atoms is called its molar mass. The mass of 1 mole of atoms changes for different elements. Here's some examples. It's 32.07 grams for sulfur, 12.01 for carbon, and 6.9 for lithium. You can find these numbers on the periodic table. The lighter the atom, the less mass in 1 mole. Suppose you want to convert from grams to moles. Calculate the number of moles we have if we're given 57.8 grams of sulfur. Given what we want to end up with. Solution map, very simple. The conversion factor then comes from the fact, if you look at the periodic table for sulfur, you see this weight for its molar mass. So 1 mole of sulfur is 32.07 grams. It's the molar mass of sulfur from the periodic table. The solution then is set up the way we normally do, the given, the conversion factor arranged so that the units cancel to get the units we want. 1.8 moles. Can we convert between moles and grams? This is something you're very often asked to do in the lab. Here I'm showing someone weighing out a specific amount in grams, but they want a certain number of moles. Calculate the mass of aluminum in 6.73 moles of aluminum. Given the moles, what you want is a gram. The map is to go directly from moles to grams using the molar mass. Molar mass is 26.98 grams of aluminum from the periodic table. Set it up, given 6.73 mole, arrange the conversion factor, and end up with 182 grams of aluminum. Converting between grams and numbers of atom. This will require 2 conversion factors. Suppose you know that an aluminum can has a mass of 16.2 grams, and you'd like to know how many atoms of aluminum there were in your aluminum can. Given 16.2 grams, and we want atoms. So the map shows that you go first from grams of aluminum to moles, and then from moles to count. This shows the central importance of moles. So here's the relationship. 20 for conversion. 26.98 grams of aluminum is 1 mole from the periodic table. 6.022 times 10 to 23 is equal to 1 mole. That's Avogadro's number. So the setup is what you're given, 6.2 grams of aluminum. First conversion. The second conversion, 3.62 times 10 to the 23 aluminum atoms in that aluminum can. Verify that you can get this result with your calculator. Converting between grams and moles of a compound requires the molar mass. Molar mass of a compound in grams per mole is numerically equal to the formula mass of the compound in atomic mass units. The formula mass of a compound is the sum of the atomic masses of all the atoms in a chemical formula. The formula mass for CO2, carbon dioxide, is found in this way. You see that you have 1 carbon, so you look up its atomic mass, which is 12.01, and then you add to it, you have 2 oxygen, 2 times the atomic mass units of oxygen, you get 44.01 atomic mass units, and then its molar mass, of course, is the 44.01 grams per mole. The molar mass of carbon dioxide is 44.01 grams per mole. So using our knowledge to convert between grams and moles for a compound, and note that a compound then is going to require the molar mass of the compound, calculated by adding up the atomic masses of all of the elements present. So we want to know the mass in grams of 1.75 moles of water. Given and find. Our map is begin with moles and end with grams, 1 conversion unit, that of the molar mass. And so we already know that the molar mass of hydrogen is twice of water is 18.02 grams, calculated from the formula. And so this then will convert us to the grams of water. Here's it shown to you. Twice the atomic mass of hydrogen, 2 times 101, and once the atomic mass of oxygen, 18.02. And so we set up and solve our problem. Given 1.75 moles of water, converted using the molar mass of water to 31.5 grams of water. Converting between numbers of molecules and mass for a compound. What is the mass of 4.78 times 10 to the 24 nitrogen dioxide molecules? Here's your given, and this is what you want to find. The map shows you'll have to have 2 conversion units, and of course the center one is going to be the mole. So we'll go from number, given, to moles using Avogadro's number, then from moles to grams using the molar mass calculated from the periodic table as 46.01 grams of nitrogen dioxide per 1 mole. Here's the setup. Here shows you the calculation of the molar mass. Again, the setup is as before, using factor label method to show that many molecules of NO2 would be a weight of 365 grams of NO2, nitrogen dioxide. Chemical formulas themselves form conversion factors. Here's the analogy. 3 leaves equal 1 clover. That's the relationship. So if you want to go from the number of clovers you have to the number of leaves, you're going to have to use 3 to 1. 14 clovers is going to have 42 leaves. The chemical formulas are conversion factors. For instance, the formula for CO2 means that there are 2 oxygens per each CO2 molecule. 2 oxygens to 1 CO2 molecule, or there's 2 dozen oxygens for 1 dozen, or there's 2 moles of O2 per 1 mole of carbon dioxide. The count ratio remains the same, whether you're talking in single atoms and molecules or dozens or moles. The conversion factor comes directly from the chemical formula. Example, 8 legs, 1 spider, 4 legs, 1 chair, 2 hydrogen atoms, 1 water molecule. How do you convert between moles of compound and moles of constituent element? You find the number of moles of oxygen in such a formula as calcium carbonate, CaCO3. So you might be given the moles of calcium carbonate and you want to find the moles of oxygen. Just 1 conversion unit needed. The one you get by looking at the formula. Looking at the formula, you can see that there are 3 moles of oxygen per 1 mole of calcium carbonate. This then is your conversion unit. Setting it up, 1.7 moles times 3 moles of oxygen for 1 gives you 5.1 moles of oxygen in that compound. Mr. Mole says to do it right. Converting between grams of a compound and grams of a constituent element. Find the mass of sodium in 15 grams of sodium chloride. This is kind of what we started out to do. Given the weight of sodium chloride, and we want to find the weight of sodium. So we go from grams of sodium chloride to moles of sodium chloride. Looking at the formula, we go to moles of sodium, and then from moles of sodium we go back to grams. This is the formula mass, molar mass of sodium chloride. This is the 1-to-1 ratio from the formula, 1 mole to 1 mole. And then again, this is the molar mass of sodium. Here's the setup. It all works out perfectly to say that you have 5.9 grams of sodium. So it turns out you're over the daily suggested limit of sodium for the day if you eat 15 grams of salt. Mole relations from a chemical formula, very easy. Just, for instance, we have carbon tetrachloride. Here's a picture of the molecule. You can see 1 mole has 4 moles of chlorine. 1 molecule has 4 atoms. 1 mole has 4 moles. The relationship is inherent in a chemical formula, and it will allow us to convert between moles of the compound to moles of the constituent element, and vice versa. Isn't that simple? Says Mr. Mole. The mass percent composition of compounds. Mass percent composition, or mass percent of an element, is the elemental's percentage of the total mass. Let's not forget that percent means mass of the part over the mass of the whole. So the mass percent of an element X in a compound is the mass of X in a sample of the compound over the mass of the sample of the whole compound times 100. Yikes, have you forgotten the meaning of percent? Finding the mass percent composition. For instance, 0.358 grams of a sample of chromium reacted with oxygen to form 0.523 grams of the metal oxide, chromium oxide. What percentage of chromium is in this metal oxide? Well, the metal oxide is the whole. It is the combined chromium and oxygen. So we already know the mass of chromium we started out with, 0.358 grams, and the mass of the whole that we ended up with when it combined with oxygen. So the part over the whole times 100 gives 68.5% chromium for this compound. Using mass percent as a conversion factor. We can use mass percent as a conversion factor between grams of an element and grams of the compound. The mass percentage composition of sodium in sodium chloride is 39%. 39% of sodium equal 100 grams of sodium chloride. Remember, percent tells you the part per 100. So these conversion factors look like this. Either 39 grams of sodium over 100 or 100 grams of sodium chloride over 39 grams of sodium. These fractions are the conversion factors between grams of sodium and grams of sodium chloride. So the FDA recommends that adults consume less than 2.4 grams of sodium per day. How many grams of sodium chloride can you consume and still be within the federal guidelines? So we have given the guideline. We can take the grams of sodium and convert it into grams of sodium chloride. And we're using the percentage as a conversion factor. We set it up like this. 2.4 grams of sodium, that's a federal guideline. Here is the percentage conversion factor, arranged so that the grams of sodium cancel. And we can have 6.2 grams of sodium chloride and be just within the FDA recommendation. Mass percent from a chemical formula. Calculate the mass percent of chlorine in this Freon 114. So you're given the formula and you want to know the mass percent. So you're going to use the chemical formula to convert to the mass percent. So first of all, we look at the formula and we can say that the amount of chlorine is 4 times the molar mass of chlorine because of the subscript 4, and the molar mass of the entire compound, so that's the part per whole. So this turns out to be 4 times the molar mass of chlorine is equal 141.8 grams, and the entire molar mass is 203.8. Calculating that, it shows that Freon 114 is 69.58% chlorine. Wasn't that great? So all matter is composed of atoms and molecules, and the formulas give us atom and mass relationships, which are very important for our understanding of chemistry.